Everyone, welcome to this lesson. So in this lesson, we're going to continue our discussion on optimization. Now, in the previous lesson, we learned what optimization is. We learned the different points that we get in terms of optimization, whether it's a maximum, a minimum, or a saddle. We talked about a special type of derivative where the derivative is equal to zero, and we classified these points as critical points. We also found out that minimums and maximums have the same first derivative. So we need a test that would classify one as either a maximum or one as either a minimum. And that test we call the second derivative test, because the second derivative is not equal for a minimum and a maximum. That for a minimum, the second derivative is positive, and for a maximum, the second derivative is a negative. So we're gonna take advantage of that fact. We also went across a special characteristic that 2D functions have, which are contour lines, which are lines where the function has a constant value. We also went through how to graph a 2D function in Excel by creating a grid of numbers. So in this lesson, I can actually go through how to analytically solve a 1D function and how to analytically solve a 2D function. So in the previous lesson, we just dealt with it conceptually. So right now, we're going to actually be doing this quantitatively. Okay, so when you're doing a 1D optimization analytically, it really boils down to two steps that you're doing. You're finding the critical points, basically where the derivative is equal to zero, and also you're enacting the second derivative test to classify whether you have a maximum or a minimum. So let's go and see how this is going to work. So the function that I'm going to be dealing with is 4 minus x squared minus 0.2 x cubed, and this is the function that you see on the side. So by visually inspecting this, we have a maxima here and we have a minima here. So the first thing that we're going to do is we're going to get the derivative of that, and the derivative of that is negative 2x minus 0.6 x squared. Now we want to find what are the x points where the derivative is equal to zero. So we're going to place this equation equal to zero. I'm going to take the x as a common factor here, and we're going to have those two factors. So one is going to be x is equal to zero, and when we place this other one equal to zero and solve it, it's going to be x is equal to negative 3.33. So we found 2 points in this function where the derivative is equal to zero. So now we go to the next step and we classify each as either a maximum or a minimum. And again, we do this by the second derivative test. And the second derivative is just a derivative of the first derivative. So here's the first derivative, negative 2x minus 0.6 x squared. If I take a derivative of that, I'm going to have negative 2 minus 1.2x. So here's my second derivative. So I'm going to evaluate the second derivative at 0. So when I evaluate the second derivative at 0, I have a negative second derivative. And we said when we have a negative second derivative, that corresponds with a maximum, and as you see here. Now I'm going to evaluate the second derivative at negative 3.33, and when I do that, I get 1.9996, and this is a positive second derivative, so we're having a minimum. So very, very simple way to deal with 1D optimization. So again, to kind of recap, we first find the critical points, basically where the derivative is equal to zero. So here's the function we're dealing with. We get the derivative function, set it equal to zero, and solve it, and we got x is equal to 0 and x is equal to 3.33. The next step is to classify these as either maximum or minimums, and this is basically getting the second derivative at these 2 points. So second derivative is merely the derivative of the first derivative, so we got negative 2 minus 1.2x, and when I evaluated this at 0, I got a negative second derivative, which means a maximum, and when I evaluated the second derivative at negative 3.33, I got a positive second derivative, which corresponds to a minimum. So this is how we deal with 1D optimization analytically. So let's actually go to 2D optimization. And how do we do this analytically? It's a little bit more involved, as you would predict, because f is now not only dependent on x, but f is dependent on x and y. And this is the same function that I introduced in the previous lesson. So f of xy, x cubed plus 3y minus y cubed minus 3x. Now, it involves the same steps. We still find the critical points, again, where the derivative is equal to 0, and we find the second derivative. But since we're dealing with two independent variables, we're going to be dealing with a derivative in respect to the first one and a derivative in respect to the second one. So if we take this function and we take the derivative in respect to x, all the terms in respect to y are going to be regarded as constants. So those are going to drop out. So this one is going to be 3x squared minus 3. So this is going to be the derivative in respect to x. And again, we're trying to get the critical points. Basically, the derivative is equal to 0. So I'm going to place this equal to 0. And when I place this equal to 0, x is going to be equal to negative and positive 1. So I'm going to do the same thing for the function in respect to y. And again, the terms that I have x will be regarded as constants. So those are going to drop out. So I'm going to have 3 minus 3y squared. Place this equal to 0. I have y is equal to plus or minus 1. So now I have 4 different combinations of xy points. I have 1, 1, negative 1 and negative 1, 1 and negative 1, and negative 1 and 1. So those are 4 points that I have the derivative equal to 0. Now when we're dealing with 1D optimization, there is a line, a tangent line, that is a tangent to these 2 points. But when we're dealing with a 2D function in general, that means there is a plane that is tangent to these 4 points. So now we have the 4 points in which the derivative is equal to 0. So now we need to either classify it as a maximum and minimum, and since we're dealing with a 2D function, we have another point that it can be, which is a saddle. Now, as you can see in this graph, we have a point here, we have a maximum here, a minimum here, a saddle here, and a saddle here. So those are the 4 points that we solved for here. Now, as with the 1D optimization, we are going to do the second derivative test. As you would predict, is going to be a little bit more involved than the 1D version. And this is the second derivative test is going to be crystallized in this h. And this h is dependent on 3 second derivatives. This second derivative and this and this. Now the second derivative is fxx, and that means I'm going to take the first derivative in terms of x, and I'm going to even differentiate it again in terms of x, and this is what fxx means. Now f of fyy, as you would predict, is basically taking the derivative in terms of y and taking another derivative of it in terms of y again. And as you predict, fxy is taking the derivative in terms of x and differentiating it in terms of y. So let's go ahead and do that. So f of x, if I take the derivative in terms of x and take another derivative in terms of x of that, we're going to have 6x. And if I take this and the first derivative in terms of y and take another derivative in terms of y, this is going to be negative 6y. And if I take the derivative in terms of x and take another derivative in terms of y, you can see all of these are going to be regarded as constants, so we have a 0 for that. Now, this h, the value of this h, is going to define what you have. And as you see in this right, here is the criteria that you have. If h is equal to 0, we need more information, okay? And those are rare cases. Now, if h is less than 0, you would classify it as a saddle. If h is greater than 0, it's either a minimum or a maximum. So you need another criteria to meet. So the other criteria that we have is down here. Is fxx or fyy are less than 0, then we have a maximum. If fxx or fyy is greater than 0, then we have a minimum. So let's go ahead and actually take those 4 points and classify them. So the first thing I want to do is I want to get fxx, fyy, and fxy. So the first thing is fxy is 0 for all of them, so we're just going to put that here. Now for the first point, 1, 1, we find that fxx, if we plug 1 here, is going to be 6. If we plug y here, is going to be negative 6, and this is 0. So if we calculate the h, it's going to be 6 multiplied by negative 6, which is negative 36, minus 0 is going to be negative 36. And based on this criteria, h is less than 0, so we have a saddle. Now for -1 and -1, well, if I have -1 here, this is going to be -6. This is still 0. And if I have -1, this is going to turn into a 6. So it's going to still give us -36. So again, we have another saddle since h is less than 0. Now, what about for 1 and -1? So if I plug in 1 for fxx, I have 6, still 0. And if I plug in -1 here, this turns to 6. So 6 times 6 is 36. So we have a positive h, so it's either a minimum or a maximum. So now we have to go down here. So the reason I said fxx or fyy, because those are usually equal. As you can see, here I have 6 and here I have 6. It's greater than 0. So both of them are greater than 0. So we have a minimum, as you can see. So the nature of this is a minimum. So how about we go to -1 and 1. So if I plug in -1 here, this turns into -6. This is still 0. And if I plug in 1, -6, right? So -6 multiplied by -6, we have 36. So h is greater than 0. Is it a minimum or a maximum? Well, fxx and fyy are less than 0. And if they're less than 0, I am dealing with a maximum. It's a little bit more involved than the 1D, but you can see is very, very simple. So kind of to recap what we did here, you find the critical point, basically where the derivative is equal to 0. And since we're dealing with a function that is dependent on two variables, we got the derivative in terms of x, then the derivative in terms of y. We set both equal to 0. We got x plus or minus 1, y plus or minus 1. Those two combined correspond to 4 points. 1, 1, -1, -1, 1 and -1, and -1 and 1. Okay, so the second derivative test is defined in terms of this h, and this h is defined in terms of those 3 second derivatives. This one is the derivative in terms of x, differentiated again in terms of x. This one, the derivative in terms of y, differentiated again in terms of y. And this one, the derivative in terms of x, differentiated in terms of y. And we found that we got those corresponding 6x, -6y, and 0. And h follows this criteria. If h is equal to 0, we need more information. If h is less than 0, it's a saddle. If it's greater than 0, it's a minimum or a maximum. We took those first 2 points, 1 and 1 and -1 and -1. It got us an h of -36 and -36, so those 2 points were saddles. So this point here and this point here. And for for 1 and -1 and -1 and 1, we've found for 1 and -1, we have a positive h, but a positive h with a positive fxx and fyy, so that corresponded with a minimum. And for -1 and 1, I have a positive h with a negative fxx and fyy, so that corresponded with a maximum. Well, so now you know how to go through a 1D optimization analytically and also a 2D optimization analytically. So in this lesson, we went through the analytical solutions when we're dealing with optimization problems. So in the next series of lessons, we're going to go through, okay, if I can't get these optimums analytically, how can I do them numerically? So we're going to go through several techniques, much like we did with previous concepts such as roots of equations and so on, to get the minima and maxima. Well, that's it for this lesson, and I will see you in the next lesson.